Welcome to Unacademy. Unacademy is the India's largest learning platform. I'm once again welcoming all to this online platform. About myself, I G Venkata. I have total 16 years of teaching experience. So far I mentored 60,000 students for GATE examination. At present I am pursuing PhD from JNTU Kakinada in VLSA domain. First we check how to get the Unacademy learning app. Just go to Play Store. There type Unacademy learning app. Type this one and click on install button. Okay, it will install the Unacademy learning app. So these are the few of the top educators from Unacademy. Here a few more. And see, recently Unacademy launched 2 batches for electrical people and ECE people. Both the batches were started from 18th of January for GATE 2022 and 2023. This is GATE 2023 for electrical students. Batch was started from 18th of January. So here it is the another batch, Spark, was started from 18th of January itself. This is for GATE 2022. Okay. So again this is a Varvi batch. This is for GATE 2023 for ECE students. And it was also started from 18th of January. And again Spark batch for GATE 2022 for triple people. So for both ECE students and electrical students, 2 batches were started. One for GATE 2022 and another one for GATE 2023. Okay, during subscription, don't forget use my code VROUT10 to get a discount. So in Unacademy, so these are the different courses they are sponsoring for GATE and engineering services: mechanical engineering, electrical engineering, ECE, electronics and communication, computer science and IT, civil engineering, production, instrumentation, chemical engineering. These are the few of the courses offered by Unacademy. So in Unacademy, there are 2 types of subscriptions: plus subscription and iconic subscription. In these 2 subscriptions, these are the benefits you are going to get. So your classes was taken by India's best educators and interactive live classes, and during live classes they will solve your problems and they will, whatever the doubts you have in the subjects, they will clarify those doubts. Okay, they will provide structured courses as well as a PDF materials to you. Okay, and the live tests they will conduct and quizzes also they will conduct. After completion of these tests and everything, they will analyze your examination paper and they will prepare a personal analysis report for you, and they will prepare some points for you for enhancing your academics and enhancing your preparation. Okay, so they will prepare a proper study plan to you especially. So by following the study plan, you will get success in your academics. See, this is about plus plan. In plus plan, for 1 month subscription, this is the cost 5,500. For 2 months, cost this much, and 6 months, 12 months, 18 months and 24 months. For third year students, this is suggestible, and for final second year students, this is suggestible. And here the beauty here is they are providing EMI option also. They are providing, and by using my code VRAW10 subscription code, you get 10% discount. Without subscription, without using code, this is the cost, but after using the code you get the cost of this one. See this, here it is 30,250. After using my code you get the cost of this one with 27,225. 10% discount you get. And for iconic plan, for 12 months, it is they are charging 50,250 rupees, and after using my code they will charge this much, 45,225. You have to pay 45,225. And EMI option also available here also, but here only two subscriptions, 12-month subscription one, and the second one is 24-month subscription, 1 year subscription and 2 years subscription. Okay, now before going to energy band diagram and intrinsic and extrinsic semiconductor, just 5 minutes I will repeat the things what we completed in previous class. Previous class we defined what is electronics, what is electronic device, what is electronic circuit, and after that we classify the materials. Electronics means it is the study of movement of electron in a semiconductor. Electronic device, it is a device which is made by a semiconductor, and electronic circuit is a circuit with at least one electronic device. That is the electronic definition for electronics, electronic device and electronic circuits. Now materials are broadly classified into three types: conductors, semiconductors and insulators. Now I am concentrating on semiconductor. Semiconductor is basically a crystalline material. So we can define a semiconductor as which behaves either conductor nor insulator based on external conditions what we provided. Default external condition is temperature. So at low temperature, in this sense 0 Kelvin, it behaves like an insulator, and at room temperature it behaves like a conductor. Okay, from the knowledge of energy band diagram we can show how it behaves like an insulator and how it behaves like a conductor here. And semiconductors are two popular semiconductors are silicon and germanium. In this, silicon is most popular. So after that we went for the classification of semiconductors. We broadly classified semiconductors into three different categories. First category is element and compound semiconductors. Second one is a direct and indirect semiconductors, and the last one is intrinsic and extrinsic semiconductors. Okay, now today we concentrate much on this. Already we completed these two. Now element means a semiconductor which is composed by similar type of atoms. A semiconductor which is composed by similar type of atoms. Example, silicon and germanium. And compound means it is the combination of different type of atoms. Gallium arsenide, gallium phosphide, indium phosphide, like that. And silicon, germanium also a combination of compound semiconductor. The purpose of using compound semiconductors is to get high speed devices and emission or absorption of light. For this purpose we are using compound semiconductors. These are some special devices we manufactured from the compound semiconductors. Gallium arsenide, by using that they prepared a laser we can prepare, and by using gallium phosphide you can design LED and gun diode, and zinc sulfate is used in television screens, and indium, antimony, cadmium, tellurium, tellurium, these are in light detectors. Okay, now I am going to next energy band diagram. To get the energy, to know about energy band diagram in detail, first you should know how our atom looks like. In an atom, nucleus is positively charged and it is placed at this center, and around of that electrons are rotating around the nucleus in an orbit. So this is the first orbit and this is the second orbit. Now here only two orbits they mention. Now this is also called outermost orbit or valency shell. This is the inner orbit. So electrons are rotating around this nucleus, around of this nucleus. Why? Because to overcome the attractive force from nucleus. and electron is rotating around of its own axis also to overcome to overcome the repulsive force from adjacent electron. Anyway, electron is continuously in movement, so once it is in movement, it possesses some energy, half mv square. So finally your electron is going to possessing some energy. Now I am going to concentrating on this energy. So let us, I am going to take this silicon semiconductor. Here is my silicon semiconductor. For silicon, atomic number is 14 and electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. First orbit, second orbit, third orbit or outermost orbit or valency shell. These two orbits are completely filled. Okay, it is very difficult to remove the electron from this and we don't have any business with these two shells. And now I am concentrating on outermost orbit. In outermost orbit we have 4 valency electrons. Okay, now all these electrons are under the influence of this nucleus. Under the influence of this nucleus, they are attracting towards this. Okay, by removing this electron, I can make that electron is a free electron. Once that electron is free electron, then that electron is useful for me to provide a conduction. Now onwards, I am going to representing the silicon atom like this. This is the silicon atom and this is the outermost orbit or valency shell. 4 valence electrons it has. Okay, now for these 4 valence electrons, we have 4 quantum numbers. If you take any 2 electrons in this, those 2 electrons are differed by at least 1 quantum number. So it represents no 2 electrons possess same energies. So the energies of these, and this is the 2-dimensional way representation of a silicon and this is the 3-dimensional representation. I'm going a little bit fast because already we completed these topics. Now this is my silicon atom. So 1, 2, 3, 4, just before we mentioned each one possesses different energy. This is the energy of first one, second one, third one and fourth electron. Similarly, I am taking another silicon atom. Both are identical to each other. Identical to each other. That's why the energy of this first electron is E1 here, E2, E3, E4. Now what I am doing is I am going to bringing these silicon atoms close to each other. Once bringing atoms close to each other, what happens is once they reach their interatomic distance, they are going to forming the covalent bond. So we called it as interacting to each other. These two atoms are interacting to each other. So according to Pauli's exclusive principle, in an interacting system, no 2 electrons possess same energy. In an interacting system, no 2 electrons possess same energy. So here also I am doing the same thing. So this electron 2, 3 and 4 are not disturbed. Previously the positions of these two, now the positions of these 3 are similar. That's why I am taking the same energy levels E2, E3 and E4. But if you observe this here, both are going to be forming covalent bond. That means they are interacting to each other. So I am going to representing these two possess different energy because from Pauli's exclusive principle. That's why its energy level is E1 dash and E1 double dash. So here what happened is initially it is posing energy E1. Okay, once bringing atoms close to each other, so while interaction their energy level is splitting like this. So this is the important point. We need this splitting. We need to estimate the complete energy band diagram of a material. See, based on that knowledge, I am going to estimating the energy band diagram of the semiconductor. So let us, I am taking n number of silicon atoms and this is a 3s energy state and 3p energy state. So outermost electron configuration is 3s2 and 3p2. This is the outermost electron configuration. Okay, now once atoms are bringing close to each other, their energy levels are splitting. Okay, and on y-axis I am taking energy and on x-axis I am taking interatomic distance. So the distance is decreasing. Interatomic distance is decreasing. Okay, so once atoms are bringing close to each other, see this here. Now atoms are identical initially. Now I am bringing atoms close to each other. once bringing atoms close to each other, their energy levels are splitting. You observed or not? Energy levels are splitting. Okay. So here both are going to be merged. Now it seems to be a single energy band. Single energy band. But so far they did not reach their standard interatomic distance. Okay, now they have to travel from here to here, this much distance, to reach their interatomic distance. So they are traveling, so that means they are bringing close to each other, much close to each other. So during that process, again their energy level is splitting. Okay, now this is my required point. So here, if you observe, in s orbit you can place 2 electrons, in p you can place 6 electrons. So such type, this is the information from a single silicon atom. So in a single atom, in s state you can place 2 electrons, in p state you can place 6 electrons, total 8 electrons you can place. Such type of atoms, here you are taking n, so you can place 2n s electrons and 6n p electrons. So these are 2n states, 6n states. Now both are merging here. Now it became 8n states. Now after that it is going to be splitting. Now at steady state, that means at 0 Kelvin, it is split into equally. So these are the upper 4n energy states and these are lower 4n energy states. Upper 4n energy states and lower 4n energy states. Okay, so now I'm going to taking this part and I'm going to highlighting that. See this, these are the upper 4n energy states and these are the lower 4n energy states. In between that, see here energy level is splitting. Here no energy level is defined, that region. Now that is called energy gap or forbidden energy gap. Okay, now see, this is the way of representing that. So this is the two-dimensional representation of our silicon at 0 Kelvin, and this is the energy band diagram of same silicon at same temperature. See, this is the covalent bond. Now that covalent bond is represented here. This is your covalent bond. Here you observe the electrons which are placed in covalent bond are the electrons from valency band. That means outermost orbit or valency shell. That's why now the electrons which are placed here with covalent bond, I am calling it as valency band. Okay, it is valency band. After that, here once increasing temperature, let us, I am going to increasing the temperature. Once I increase the temperature, covalent bond will break, this electron will come out of it. So this is the electron is coming out of it by breaking this covalent bond. Now here a vacant position is forming, that is, we called it as a hole. Okay, now this is called free electron. Now this electron is useful for conduction. Because of that, this space I am calling it as conduction band, CB, conduction band. So the minimum energy level of conduction band is EC and maximum energy level of valency band is EV. Okay, so this is the basic information about its energy band diagram. Now see, at 0 Kelvin this is the case. At 300 Kelvin, what happens? Covalent bonds will break. Electron is moving from valency band to conduction band. Okay, so here what we are doing is, once you are going to be increasing temperature, electrons are moving from valency band to conduction band. Okay, this is called thermal generation. Thermal generation. This process is called thermal generation, because by increasing temperature you are going to increasing the number of charge carriers. So this process is called thermal generation. Okay, so you may ask one thing, sir, I am going to increasing temperature from 300 Kelvin to 350 Kelvin or 400 Kelvin, then what is the case? Nothing. Once temperature is increasing, more number of covalent bonds will break, and this electron is moving here, and it is moving, it is moving, it is moving. If you are increasing temperature again much, now more covalent bonds will break. Only that is the case. Okay. Next, direct and indirect semiconductors. This is the second class of semiconductors. So this is the previous case. We draw the energy band diagram with a neat straight lines. But practically, if you are going to the semiconducting material complete semiconducting material, energy band diagram is not like that, straight lines. It is not like straight line. Okay, so it is like with some variations. See, like this, like this. Now this is EC. This is going to be EC, and it is going to be EV. And this is our semiconductor, complete semiconductor. Okay, now previously we observed, once temperature is increasing, electron is moved from valency band to conduction band. Once electron is moving from valency band to conduction band, okay, now these here 3 electrons you have in this case, but the available energy levels are 4n energy states. So that electron is moving freely in conduction band. Okay, now for example, let us 2 electrons try to occupy the same energy level. 2 electrons try to occupy the same energy level. In that case, there is a collision between those 2 electrons. Okay, the resultant of that collision is one electron is going to occupy the defined energy level, and other electron is returned back, fall from conduction band to valency band, and it again forming the covalent bond here. Now see, here electron is falling from higher energy level to lower energy level. Now the difference of energy will come out in the form of either light or heat, any one of this. So which one is coming at output, either light or heat? Which one? To define that, you need to know about propagation constant. It explains about how the movement of carriers in a semiconductor, how carriers are moving within a semiconductor. See, now I'm going to plotting this. On x-axis, y-axis I am taking the energy, and on x-axis I am taking the propagation constant K. This is the case. The minimum energy level of conduction band and maximum energy level of valency band both are present at same K value. And this is the another case where the minimum of EC and maximum of EV both are at a different K value. It is let us K1, and here it is, let us take it as K2. Both are at different K values. Okay. Now once electron fall from higher energy level, that means conduction band to valency band, here the difference of energy will come out in the form of a light. And here, to move the electron from conduction band to valency band, first it is going to occupy the temporary energy level, and then it will return back from the temporary energy level to valency band. Temporary energy level to valency band. Now here change in K takes place, that means change in propagation constant takes place, and Propagation constant is directly proportional to momentum. Sorry. So once it is a directly proportionality between these two, so once k value changes, momentum also changes. Once momentum changes, the difference of energy will come out in the form of a heat here, and here the difference of energy will come out in the form of a light here. So this is called a direct band gap semiconductor or a direct semiconductor. Example for this one is gallium arsenide. Gallium arsenide is the example for this, and this is called indirect band gap semiconductor or indirect semiconductor. Example is silicon, germanium. Okay, silicon and germanium comes under this category. So this is about your direct and indirect semiconductors. So because of that only in your IC, once you are using your IC or for example take your processor, in your CPU, behind of your CPU backside there is a fan rotating. The purpose of keeping that fan is it is going to continuously cooling your processor. Okay, there is a processor, upon that they place heat sink and upon that they place the fan. Okay, heat sink is going to whatever the heat generated by that processor, because the processor is designed by a semiconducting material, silicon. Okay, so once it is operating that, during this transition, this type of transition, heat is coming out. Okay, now to cool that we are using heat sink, and additional cooling solution we provide is fan. Okay, this is about your direct and indirect semiconductors. Okay, next one is we are going to intrinsic and extrinsic semiconductors. Before going to intrinsic and extrinsic, I want to discuss one important point. Whatever the fourth group we have, fourth group elements having an important place. If you verify the fourth group elements, carbon, silicon, germanium, tin and lead. Here carbon is available in two forms, diamond and graphite. Okay, diamond is insulator and graphite is semiconductor, and we know that silicon and germanium are the semiconductors and these two are the conductors. The beauty of this fourth group is, okay, the classification of materials we done as conductors, semiconductors and insulators. See here conductors are there, next here semiconductors are there, here insulator is there. So that is the beauty of the fourth group. Okay, all type of materials are present in this. And one more important point regarding this graphite is, now much research work is going on graphite based devices. Okay, if they get success in that, in future you get your laptop like your pen. The way how you are carrying your pen, the similar way you can carry your laptop, because graphite having the folding property. Okay, once they design your laptop by using the graphite, you can fold it. So whenever you want to use that, you can stretch it, keep there, and you can operate it. Okay, so these are the two semiconductors we have, silicon and germanium. So the beauty of fourth group is it is going to covering all type of materials. Okay, now I am going to first intrinsic semiconductor. How can you define an intrinsic semiconductor? Whatever the semiconductor we have, the pure form of that semiconductor is called intrinsic semiconductor. So pure form of semiconductor is called intrinsic semiconductor. Okay, now once the semiconductor is available in pure form, already we defined semiconductor which can behave like either conductor nor insulator. Okay, in insulator point of view, no need to do much analysis. Okay, in SiO2, silicon is available as an insulator in the form of SiO2. We discussed about that one in MOS transistor. Now about conductor. Now my intention is to use my silicon or semiconductor, that too intrinsic semiconductor, as a conductor. Once I decided to use my intrinsic semiconductor as a conductor, it is unable to produce the amount of conductivity produced by a regular conductor. For example, regular conductor is going to providing this much conductivity. Okay, so your intrinsic silicon is going to provide only this much conductivity. Okay, insulator conductivity is here, ground level. Okay, conductor level is here. This is the conductivity of conductor, regular conductor, and this is the conductivity of intrinsic semiconductor. See how much gap it is. I want to reduce this gap. That means I want to increase the conductivity of a semiconductor. That is my intention. Okay, now for that, first I am going to checking conductivity of a semiconductor depends on which parameters. See this. Conductivity is represented by sigma. It depends on temperature, intensity of light, and impurity. It depends on these three parameters: temperature, intensity of light, and impurity. Now I check one by one option. First, temperature. I am going to start increasing temperature. Previously we observed, once increasing temperature, covalent bonds are breaking. Once covalent bonds are breaking, we are getting more number of charge carriers. So once more number of charge carriers are available, okay, you get more conduction. Okay, but the process of increasing temperature to increase the conductivity is not suggestible practically. Why? Because at high temperatures, there is no guarantee the material retain its original state. The properties of the material is going to be changing at high temperature. That is the problem. So because of that, the method of increasing temperature for increasing conductivity is not suggesting. So one method is not useful to us. So I am not suggesting this method. Next, going to next one, intensity of light. So intensity of light is equal to energy h nu. So light also a sort of energy. It gives energy in the form of photons. Once we place the photons on a semiconductor, whatever the covalent bonds we have, see here, if I take a semiconductor, it is silicon and here another silicon, so covalent bond. So another covalent bond, another covalent bond. These are the covalent bonds. Silicon, silicon, silicon. Now, once I place the light, once I place a light here, this covalent bond will break, electron will come out of that, because light is nothing but a sort of energy. Okay, now covalent bond will break, electron will come out of that. To get more conductivity, you need more number of charge carriers. To get more number of charge carriers, more intensity of light you have to be placed on that. Okay, getting more intensity of light is a costly process. So this is costly process. Because of that, I am going to not suggesting this method. Okay, so remaining is impurity. Just we go and check this impurity. Let us take a milk. Very few people drink the milk as it is. Majority of the people drink the milk by adding sugar into that. Sugar, boost, something. The thing what you are adding into that to that milk, by adding that one into that, it will increase the taste as well as it will provide strength. Okay. Now, after adding the impurity to that, to the milk, that means adding sugar to the milk, the property of taste of the milk was changed. The same way, here I am taking the intrinsic semiconductor and I am adding impurity to that. I am adding impurity to that. Here the purpose of adding impurity is just to increase its conductivity, not more than that. Here the intention behind the adding impurity to intrinsic semiconductor is to increase its conductivity. Here now see, here we have intrinsic semiconductor, intrinsic semiconductor, intrinsic semiconductor. So for this I am adding impurity, impurity I am adding to that. After adding impurity, it became extrinsic semiconductor, extrinsic semiconductor. Now here the intrinsic semiconductor is either silicon or germanium. You can take any one of this. And the impurity what you are adding is either you can add third group impurity or fifth group impurity. You can add third group impurity element or fifth group impurity. The third group impurity elements are boron, aluminium, gallium, and indium also is there, but because of large size of indium, atomic size, it is not preferred. And in fifth group, phosphorus, arsenic, antimony. These three we are using. Here mostly boron, some cases aluminium and gallium. Here phosphorus, arsenide. Now after this, for silicon or germanium, that means for intrinsic semiconductor, if you are adding third group impurity, resultant material is, you called it extrinsic semiconductor. This is also extrinsic semiconductor. Now here, based on the impurity, I am going to be classifying this extrinsic semiconductor into two types. For third group, by adding third group, you get p-type extrinsic semiconductor. And by adding fifth group impurity, you get n-type extrinsic semiconductor. Now simply we called this is a p-type semiconductor and we call it as n-type semiconductor. So p-type and n-type semiconductors are extrinsic semiconductors. Extrinsic semiconductors. Okay. Now, so this is the way of order of increasing the conductivity. These are the insulators. Insulators conductivity is low. Semiconductors conductivity is moderate. And here conductors conductivity is high. Now, so now we are going to entering into the impurity. So the process of adding impurity is called doping. Here I will give some important terminology I will share. First one is doping. Doping. What is doping? Doping is nothing but the process of adding impurity to an intrinsic semiconductor is called doping. You are adding impurity to intrinsic semiconductor to increase the conductivity of intrinsic semiconductor, and that process of adding is called doping. That process of adding is called doping. Here, now onwards, we are going to using less doping, high doping, moderate doping. If you take your BJT, emitter is heavily doped, base is lightly doped, collector is moderately doped. So now onwards we are going to using this term frequently. Okay, now you are going to adding impurity. Fine. I am going to taking first silicon crystal. This is the silicon crystal. Here I am taking three-dimensional representation of it. This is the silicon crystal. So this is the silicon crystal. Here first I am going to taking 1 unit volume of silicon crystal. In this 1 unit volume, here it is 1 unit volume. This is 1 unit volume. This is 1 unit volume. And intrinsic carrier concentration. So it is nothing but a number of charge carriers per unit volume. The units for this one is per centimeter cube or per meter cube. Per centimeter cube or per meter cube. Okay. Now here doping. Doping also represented by per unit volume. So in terms of concentration. So the concentration of doping is this much. For example, doping concentration is 2.5 into 10 power 18 per centimeter cube. Atoms per centimeter cube or per centimeter cube. It means this much amount of impurity you are adding per this unit volume of space. Adding to this. That is the meaning of this. Here you are adding. Okay. For 1 unit volume you are adding this much impurity. Okay, here 10 unit volumes you have, for example. So into 10, this much impurity you need to be add. Like 1 spoon of sugar for 1 cup of milk. So 10 cups if you are using, 10 spoons you need to add. Okay, so this terminology, concentration and doping, you should be thorough with this. Okay, so N represents electron concentration. It means number of electrons per unit volume of space. P, hole concentration, number of holes per 1 unit volume of space. And Ni, intrinsic carrier concentration. So what is this intrinsic carrier concentration and everything we discuss later. Next it is coming. Okay, now see, this is intrinsic carrier concentration. And one more, in intrinsic semiconductor, electron concentration equal to hole concentration equal to Ni. Why it is Ni, everything we discuss later. Next it will come. And a little bit time I go back to energy gap. Already we drawn the energy band diagram. We have idea on this. So this is the conduction band. This is the valency band. Here it is EC, minimum energy level of conduction band, and it is EV, maximum energy level of valency band. maximum energy level of valency band. Now EC minus EV, we call it as energy gap EG. Okay, so EG is an EC minus EV, and it is the function of temperature. Okay, if temperature changes, that energy gap is changing. So by increasing temperature, energy gap is decreasing. Okay, decreasing. Now, for silicon, this is the equation for energy gap. Energy gap for silicon is 1.21 minus 3.6 into 10 power minus 4 into T. T is absolute temperature. So 1.21 minus 3.6 into 10 power minus 4 into T, electron volts. Here energy is represented in terms of electron volts. And for germanium, energy gap is 0.785 minus 2.23 into 10 power minus 4 into T electron volts. Okay. Now, this table is very important, sir. Previously, they asked more or less in all competitive exams, they asked the question on this table. So, at room temperature 300 Kelvin, what is the energy gap of a silicon? Just to substitute 300 here. Substitute 300 here. By substituting 300 here, you get 1.102 electron volts approximately. Now I am taking that is approximately 1.1 electron volt. Okay, just if you substitute 0 here at 0 Kelvin, it is 0, T0. Now this whole thing became 0. So it is 1.21 electron volts. Similarly for germanium, at 0 Kelvin, energy gap is 0.785 electron volts. And at 300 Kelvin, it is 0.72 electron volts. Okay. Okay, sir. So this is the energy gap for silicon and germanium. Okay. And one more important thing. So far you are using the energy and you are representing that energy in terms of joules. Okay. Now this is the relation between joules and electron volts. See, 1 joule is equal to 6.25 into 10 power 18 electron volts. And 1 electron volt is equal to 1.602 into 10 power minus 19 joules. So sometimes they will give the data in terms of joules energy. So at that time you need to convert that energy in terms of electron volts. So during that conversion you can use these values. Okay, so this is the energy gap. And if you take the gallium arsenide energy gap is 1.43 at room temperature. 43 electron volt at room temperature. 1.43 electron volts at room temperature for gallium arsenide. This is upcoming technology, sir. This is for okay, electron volts it is in. Electron volts. And just before I mentioned silicon dioxide, it is the insulator. Its energy gap is 9.0 electron volts at room temperature. Okay, so you should be thorough with these 4 values. Most importantly, these 2. Okay, so while solving problems, you need to use this. Sometimes in exam, they may to get the approximate value, you can use these values. Next, N-type semiconductor. Now I am entering into extrinsic semiconductors. I am entering into extrinsic semiconductor. Okay, how to get extrinsic semiconductor? Okay, now let us first I am taking N-type semiconductor. N-type semiconductor. The first step is just take the intrinsic semiconductor what you have. Now in this, these are the silicon atoms in this because it is intrinsic semiconductor. Okay, intrinsic semiconductor. In this, next I am going to adding impurity to this. I am adding impurity to this. So the impurity what I am going to adding is fifth group element. Let us adding phosphorus. After adding impurity to this, what happens is few of the silicon atoms are replaced by this impurity atoms. Now let us, it is replaced by impurity atom. Okay, for better understanding, I am going to increasing the size of this. Okay, let us take this is a semiconductor. So here we are going to adding the phosphorus. Impurity we are adding, that is phosphorus. So initially these are the intrinsic semiconductor. So all these are silicon atoms. All these are silicon atoms. Silicon atoms. After adding this impurity of phosphorus to this silicon atom is replaced by phosphorus. The same way this silicon atom is replaced by phosphorus. It is replaced by phosphorus, replaced by phosphorus, replaced by phosphorus, like that. Few of the silicon atoms are replaced by phosphorus. That is the first step. Okay, and this is at 0 Kelvin. That is very important. Now I want to represent the same thing in a energy band diagram point of view. I want to represent the same thing in a energy band diagram point of view. So now this is the energy band diagram of a intrinsic semiconductor at 0 Kelvin. Intrinsic semiconductor at 0 Kelvin. This is EV and it is EC. Is EC. At 0 Kelvin, all covalent bonds are completely filled in valency band. All covalent bonds are completely filled. All covalent bonds are completely filled here. Yeah. Now, same thing we take in the two-dimensional representation. This is the two-dimensional representation of silicon. And between these there are covalent bonds. Here, here, one more. Yes. So these are the covalent bonds. So the temperature is at 0 Kelvin. Don't forget that. So these are the electrons. For this silicon atom, 4 valence electrons. For this 4 valence electrons. Like this. Now, so temperature is 0 Kelvin. So your semiconductor is like this. So no free charge carrier is available to you. Okay. Now for this silicon sample, what we done? Just we added impurity of phosphorus to this. After adding phosphorus to this, what happened? Few of the silicon atoms are replaced by impurity atoms like this. Now I am going to taking this portion. I am going to magnifying this portion here. Let us, this silicon sample is, this is replaced by phosphorus. Let us, it was replaced by phosphorus. But in phosphorus, only 3 electrons it has. This is, here we have 1 electron. Phosphorus having 3 valence electrons. So first 1 electron, second one and third one. So this is the 4th electron for silicon previously, but here we don't have that electron. There is no electron there. So here is a vacant position of electron. Here is a vacant position of an electron. Okay. Now this vacant position is related to phosphorus. Okay, now the energies of all these things we mentioned, this covalent bond we mentioned, all these things we mentioned, but this vacant energy level we did not mention. Now the vacant energy level is close to the conduction band. Just a minute. So vacant level. Okay, now we are adding phosphorus. Now that, sorry sir, phosphorus is a 5th group element. Sorry, it has one more excess electron. Sorry. Yeah, little bit confused. Now see, phosphorus 4 valence electrons and one more excess electron it has. This is the excess electron, because now phosphorus is having 1, 2, 3, 4, 5 valence electrons. 4 valence electrons forming covalent bond with 4 adjacent silicon atoms, and 1 excess electron is there. But now this excess electron is not under the bonding, but that electron is under the influence of the phosphorus. Under the influence of this phosphorus. By providing a little bit energy, I can move this electron away from it. That means I can make this electron as a free electron. That means without any impact on this electron from this phosphorus atom. Okay. Now this electron, what we mentioned, excess electron, energy is going to be, all these excess electrons are represented here by energy level. This new energy level is called ED, donor energy level. And the electrons which are placed here, excess electrons, this is the electron from this phosphorus atom, and this is the electron from this phosphorus atom, and this is the electron from this phosphorus atom, and this is the electron from this phosphorus atom, and again this is the electron from this phosphorus atom. All these excess electrons are going to occupy the same energy level. Immediately you have to ask one question. Sir, just before you mention, according to Pauli's exclusive principle, in an interacting system, no two electrons possess same energies. But again you are saying all electrons are occupying the same energy level. Yes, again I am saying the same thing. Pauli's exclusive principle is applicable to an interacting system. Here, this phosphorus atom and this phosphorus atom both are not interacting. This one and this one both are not interacting, both are identical. The way how we mentioned identical silicon atoms previously, two identical silicon atoms, energy E1, E2, E3, E4, the same way these electron here, this electron here, both are identical. There is no interaction between this phosphorus atom and this phosphorus atom. This phosphorus atom is interacting with adjacent silicon atoms. This way how this phosphorus atom interacting with adjacent silicon atom, the similar way this phosphorus atoms also interacting with adjacent silicon atoms. This one, this one, this one, this one. All are identical phosphorus atoms. Now, because of that, the energies of this electron, this electron, this electron, this electron and this one are at the same energy level. Okay. Now, this is the energy band diagram of N-type semiconductor at 0 Kelvin. If you observe this once, there is no free electron available in conduction band and no hole available in valency band. Because of this, no electron in conduction band and no hole in valency band, it behaves like an insulator. So, not only intrinsic semiconductor, extrinsic semiconductor also behaves like an insulator at 0 Kelvin. Okay. Now you may ask one thing. Sir, I am going to increasing temperature. Then what happens? And before that, what sir, these electrons are not providing any conduction? It will provide. But these electrons, first you need to bring those electrons out of the influence of this phosphorus atom. Now these electrons are under the influence of this phosphorus atom. First you need to bring those electrons out of that phosphorus atom. That means you need to move your electron from here to conduction band. Okay. Now for that you need to apply some energy. This is the amount of energy you need to apply. Okay. That energy is called ionization energy. Just a wait. So now we are on EC minus ED. So this is N-type semiconductor. So EC minus ED. We know energy gap EC minus EV. Let us take for a semiconductor silicon. At 0 Kelvin, that's value is 1.21 electron volt. Okay. Now, how much it is? EC minus EV is how much? Okay. Now, that is going to be changing from material to material. That depends on the amount of impurity what you are going to be added to that. Okay. Now, let us take some impurities. Okay. Now, for phosphorus, I am writing that values here. For phosphorus, First of all, this EC minus ED is called ionization energy. Ionization energy. Ionization energy. That means why it is called ionization energy is phosphorus, by giving one electron, that means it is giving free electron to you. It is donating one electron to you for conduction. That means you are making this electron free from the influence of this phosphorus. That's why one electron. Okay, by giving one electron to you, it became positively charged. It became ionized. So to make your phosphorus atom into ionize, you are applying this much energy. That's why it is called ionization energy. Ionization energy. Okay, and this ionization energy is different for different materials. For phosphorus, arsenic, antimony, mostly we are using these materials. Okay, now for phosphorus, its value is 0.04 because it is a very low value, milli electron volts. So it is 0.044 electron volts. That means 44 milli electron volts, and it is 0.049 electron volts in case of arsenide, and in case of antimony 0.039 electron volts. That is the ionization energy for n-type impurities. These are called n-type impurities, and by providing temperature, by providing this much external energy, you are moving this electron from here to here. Okay, so that means this your phosphorus is going to be donating one electron to you for conduction purpose. That's why n-type semiconductor also called as donor semiconductor. Donor semiconductor. And the impurities what you are adding here, phosphorus, arsenic, antimony, these are called donor impurities. Donor impurities. Donor impurities. And the amount of impurity what you are adding is represented by the term ND, donor impurity per centimeter cube. This is the concentration of impurity. Concentration of donor impurity, ND. Concentration of donor impurity, ND. Okay. Now, what I am going to do is, now I want to increase temperature. That means I am providing this much energy. So, at 0 Kelvin, we know how our n-type semiconductor is. Okay. It is like this. Now I am going to increasing little bit temperature, but not up to room temperature. If I increase room temperature, these covalent bonds will break and electron is moving from valency band to conduction band. Okay. So, now, just a minute, it is streaming. So just a minute, I will once again I will drag upload this. Now see, don't waste time. Now here 300 Kelvin is required to break the covalent bond and move the electron from valency band to conduction band. So by providing 300 Kelvin, how much energy you are providing? In case of silicon, it is 1.21 electron volt. Just 1 minute, sir. I will open that once again. Yeah. See, so this is conductivity. Yeah, this is n-type semiconductor. Okay. Now, here, just before we mentioned the values. So this is the, for phosphorus, it is 0.044 electron volts. And for arsenide, we mentioned it as 0.049 electron volts. And for antimony, it is 0.039 electron volts. Okay. Now, just to compare one thing here. So, regularly at room temperature, you are providing this much energy to break the covalent bond on moving electron from valency band to conduction band, 1.21 electron volts. Here 0.044, 0.044, 0.049, 0.039, average I can take it 0.05 electron volts approximate. See, just to compare to this, how much less it is. Okay, so less amount of energy is sufficient to move this electron from here to here. Okay, so 300 Kelvin is not sufficient. 300 Kelvin of temperature is not required to make an extrinsic semiconductor into a conductor. Now I am going to that one only. Here, see this. So this is a insulator at 0 Kelvin. These are the electrons from phosphorus. Now at 100 Kelvin, just I am going to increasing temperature up to 100 Kelvin. So once increasing the temperature up to 100 Kelvin, this 100 Kelvin of temperature is sufficient to provide an energy of 0.05 electron volts, what we call as ionization energy, EC minus ED. This is our ED, donor energy level. So at that point of temperature of 100 Kelvin, your electron is moving from here to here. It is moving here to here, here to here, here to here. Now some electrons are available in conduction band. Okay, now, but there is no hole. So no hole in the sense that you can't say P is equal to 0, hole concentration equal to 0. You can't say like that. Here more number of electrons. So that means N greater than P. Because of these electrons, it behaves like a conductor. Okay. Now I am increasing temperature up to 300 Kelvin. 300 Kelvin. At 100 Kelvin itself, the electrons already which are placed here are moved from here to here. Now at 300 Kelvin, these covalent bonds are breaking additionally. Now electron is moving from valency band to conduction band. Now here see clearly, 8 electrons, 4 holes. So N again greater than P. So and it behaves like a conductor again. And compared to the conduction in the previous case, in this case conduction is increased. Okay, that is the important point. Like this, by increasing the temperature, your extrinsic semiconductor conductivity is increasing with respect to compared to intrinsic semiconductor. Okay, so at 0 Kelvin, it behaves like similar to intrinsic semiconductor as an insulator, but at room temperature it is a conductor, but the conductivity is more than the insulator because of these additional electrons. These additional electrons we get from phosphorus by adding phosphorus impurity to that. Okay, and you may get one doubt here. Sir, once electron is moving from here to here, we got a hole. Same way, once electron is moving from here to here, why don't you get a hole here? No, you are not getting any hole here. Why? Because You are getting hole in this sense. This is the breaking of covalent bond. It is the covalent bond. Once electron is moving from out of the covalent bond, that means by breaking covalent bond, you are moving your electron from valency band to conduction band. Valency band to conduction band. Okay. So breaking of covalent bond is there. Here, there is no breaking of covalent bond. Okay, this electron is placed here. Your phosphorus forming covalent bond with 4 adjacent silicon atoms, and your electron is here. This is the excess electron. Okay. Okay, sir. So that's why there is no covalent bond formation here. So this is the complete energy band diagram of a n-type semiconductor. Okay. Now, how can we represent an n-type semiconductor? Because why means every time it is difficult to us to represent n-type semiconductor like this, Okay, this is the way of representing n-type semiconductor. I will explain that once again. Just a minute. I will draw it in a separate sheet. Here, see this. Let us take first intrinsic semiconductor. Intrinsic semiconductor. In intrinsic semiconductor, we have plenty of silicon atoms, because all are similar type of atoms. So once all are similar type of atoms, no need to specify that atom. Okay, those things. Now, at room temperature, first initially it is intrinsic semiconductor. In intrinsic semiconductor, at room temperature, few holes and electrons are present. This is hole, this is electron. This is hole and this is electron. Hole and electron. And we know that number of electrons and holes in an intrinsic semiconductor is equal. This is hole and this is electron. Hole and electron. Let us. I will show why these number of electrons and holes are equal in intrinsic. See this. This is intrinsic semiconductor. This is EC and EV. At 0 Kelvin, all covalent bonds are completely filled. At 0 Kelvin. Now I am going to increasing temperature from 0 Kelvin to 300 Kelvin. Once increasing 0 to 300, now this covalent bond will break. Electron is moving from here to here, and it is also moving here to here, and it is also moving from here to here. So you observed 1, 2, 3. 3 electrons are available here and 3 holes are available. That means electron concentration equal to hole concentration. What we are calling it as intrinsic carrier concentration Ni. Intrinsic carrier concentration Ni. So this is intrinsic semiconductor. Number of electrons is 4. Number of holes equal to 4. That means N equal to P equal to Ni. Okay. Now, after that, I am adding phosphorus impurity. Once you are adding phosphorus, it became P plus and it provide one free electron to you. Okay. Now, this is P plus positive immobile ion. P plus positive immobile ion. P plus, because these impurity atoms are very less in number. That's why I am going to representing those numbers. This is P plus and it will provide one free electron to you. So these are the free electrons provided by this. Okay. Now, so here just I am going to removing 2 holes. Later I will explain why I removed these holes. Now this is the way of representing. Now it became n-type semiconductor. N-type semiconductor. Now here This is positive immobile ion. Immobile ion. And it is hole. It is, and this is also free electron. Free electrons. They are the free electrons, and this is the hole, and this is positive immobile ion. There is a much meaning in this, and we can call it as, can also be called as, so n-type semiconductors are donor impurities. So donor ion, positive donor ion, donor ion. Okay. Now the amount of doping what we done is Nd per centimeter cube. Amount of doping is Nd per centimeter cube. Donor impurity concentration. Nd is donor impurity concentration. Donor impurity concentration. Nd is. Okay. So this is immobile, like your landline. Like your landline you can't move from one point to another point, one house to one home to another home, you are not moving. Okay, that means why? Because your phosphorus is going to be forming covalent bond with 4 adjacent silicon atoms. It is tightly bonded by these 4 sides, from 4 sides with the silicon atoms. Okay, that's why it is immobile, not moving. Immobile, not moving. And ion, because it is providing 1 electron to you. By providing 1 free electron to you, it became positive immobile ion. Okay. See, if you understand this concept thoroughly, it is helpful to you in the analysis of PN junction diode and transistor. Okay. While junction is open circuited, this much information you get. And that junction is open circuit. And during formation of the PN junction diode, you get this much information. Plenty of information you get from PN junction diode when it is forming, junction is forming, and after junction is formation. Okay. Now, during that process, you need to know how to represent p-type semiconductor and how to represent an n-type semiconductor. Okay, what is the meaning of each and every element present in that? So total 3 elements are present in this: positive immobile ion, holes, and free electrons. This is the way to represent n-type semiconductor. Okay. Next, I am moving to p-type semiconductor. Okay. Same way. So by adding third group impurities like boron, aluminum, and gallium to an intrinsic semiconductor, it became p-type semiconductor. After adding impurities, see this is semiconductor. Okay, semiconductor. After adding impurities, these are the silicon atoms. After adding impurities, similar to previous case, n-type semiconductor, few of the atoms are replaced by impurity atoms. Let us, I am going to adding boron. Let us, somewhere here boron, somewhere here boron, somewhere here boron. Okay, so some of the silicon atoms are replaced by impurity atoms. Okay, now if you take the boron, by taking 1 electron, because valency number of valence electrons in boron is only 3. Electrons is 3 only, valence electrons. Now by taking 1 electron, it became B minus, and that too Here your boron is going to be tightly bonded by 4 adjacent silicon atoms, similar to n-type semiconductor, phosphorus in n-type semiconductor. Okay, so by taking one electron, it is going to provide B minus. Just taking electron in this sense, there is a vacant place. There is a vacant place, vacant space. That vacant space of an electron, we called it as hole. That vacant space of electron, we called it as a hole. That means it is accepting one electron. That's why these are called acceptor impurities. Acceptor impurities. Okay, and p-type semiconductors are also called as acceptors. Acceptors. This is the energy band diagram of it. At 0 Kelvin, whatever the vacant energy level we have here is going to be represented here. This is boron, sir, not silicon. It is boron. Two-dimensional representation of silicon crystal. Initially it is. Now I replaced that one with a boron. That means I am taking only this part. This part. I am representing that portion here. Boron. Now surrounding of that, it is covered by silicon atoms. One vacant energy level is available, that is hole. From this boron, this is the hole provided by that, and this boron provided by this hole, and this hole provides this hole, and this boron provides this hole. Similar to the previous case, these boron atoms are identical to each other because all boron atoms are surrounded by plenty of silicon atoms. Each atom is surrounded by 4 atoms, but in between boron, see, some of the students are facing problem here. So once you are representing boron impurity, boron impurity, boron impurity here, in between this, what we have, in between boron to boron, you have plenty of silicon atoms, plenty of silicon atoms, plenty of silicon atoms. Okay, in between. Okay, it is not possible to represent. That means it is very difficult to represent all the covalent bonds, all the silicon atoms in that. Okay, instead of representing very high, huge number of silicon atoms, it is, for me, it is very easy to represent few number of impurity atoms. That's why I am representing only impurity atoms. Okay, so this is the case at 0 Kelvin. Okay, here no electron is available in conduction band, no electron here, and no hole is available in valency band. That's why at 0 Kelvin, p-type semiconductor behaves like an insulator. Okay, similar to the previous case, here also I am going to increasing the temperature level by level. First at 0 Kelvin, this is the case. So no electron here and no hole here. It behaves like an insulator. Next at 100 Kelvin. At 100 Kelvin, this is the energy. And one more, this energy level, what we mentioned here is called acceptor energy level EA. Previously we defined EC minus ED is ionization energy. Here EA minus EV is ionization energy. EV is ionization energy. Ionization energy. Okay, the generally using p-type semiconductors here we are boron, aluminum and gallium. For these materials, the value of this ionization energy is, for boron it is 0.045 electron volts, and for this 0.057 electron volts, and for gallium it is 0.065 electron volts. So ionization energy of this one is for this p-type semiconductors is, in case of boron it is 0.045 electron volts, In case of aluminum, it is 0.057 electron volts. In case of gallium, it is 0.065 electron volts. Okay, so to provide, actually in case of silicon, energy gap we have 1.21 electron volts. Compared to this 1.21 electron volts, these values are very small. To provide this much energy, okay, this much energy, very less amount of temperature is sufficient. So let us, I am increasing temperature up to 100 Kelvin. So at 100 Kelvin, these covalent bonds are breaking. That means they are attaining this much energy by thermally. Okay, now they are moving from here to here, here to here, here to here, here to here. Here no electron is available, and but holes are available here. So hole concentration is greater than electron concentration. Hole concentration is greater than electron concentration. Okay, so once charge carrier is available, it behaves like a conductor. Similarly, now I am increasing temperature up to 300 Kelvin. At 300 Kelvin, so additional covalent bonds will break. Now the electron will move from valency band to conduction band. Valency band to conduction band. That means at 300 Kelvin it is going to attain whatever the energy you need, 1.21 electron volts. It will attain this energy and covalent bond will break. It is moving from here to conduction band. Now if you observe, here total 8 holes are there, but here only 4 holes are left. 4 electrons are available. That means hole concentration is greater than electron concentration. Hole concentration is greater than electron concentration. Okay, hole concentration is greater than electron concentration. Okay, now similar to N-type semiconductor, how can we represent a P-type semiconductor? Okay, in N-type semiconductor, we have positive immobile ions. Okay, similarly, in P-type semiconductor, we have negative immobile ions. This is my P-type semiconductor. So negative immobile ions it has. These are boron ions, negative boron ions. Each boron ion required one electron. That means vacant space is available. That is nothing but a hole. Each one provides a hole to you. Hole. Next one is here at the intrinsic time. Intrinsic time, that means without doping, it has electrons and holes. So electron and hole, electron and hole. Okay, just a minute, I will change the color. Here this is a hole and electron. Okay, hole and electron and hole. I will represent later why it is not representing electrons here. Now this is the way of representing P-type semiconductor. In this, here this is going to be hole and this is also hole. Hole it is. And this is negative immobile ion. Negative immobile ion. Okay. Negative immobile ion. Okay, next one is, this is going to be free electron. Free electron. Okay, so this is free electron, hole and negative immobile ion. These are the different elements present in a P-type semiconductor. P-type semiconductor. So far we know how to represent N-type and P-type semiconductors. Okay. From the knowledge of this, I am going to preparing what are the majority charge carriers and what are the minority charge carriers in each and every semiconductor. Okay, here it is a type of semiconductor. Type of semiconductor. Okay. And this is majority carriers. Majority carriers. Here it is minority carriers. Minority carriers. Okay. So type of semiconductor. Oh, sorry. So type of semiconductor is N-type and P-type. N-type and P-type. So here this is here majority carriers. Majority carriers. And here it is minority carriers. Minority carriers. In N-type semiconductor, majority charge carriers are electrons. Electrons. And minority charge carriers are holes. In P-type semiconductor, already you mentioned majority charge carriers are holes. That means there you mentioned P greater than N. In P-type, you written P greater than N. Okay. In N-type, you written N greater than P. N greater than P. N greater than P. Okay. And here, these are electrons. Minority charge carriers here are electrons. Electrons. Okay. Electrons. So this is very important, sir. As electronic student, you should know what are the majority charge carriers and what are the minority charge carriers in a semiconductor. Okay. Now here I am going to giving a little bit problem, just very small. Let us, I am taking first intrinsic semiconductor. Intrinsic semiconductor. Intrinsic semiconductor. Now its carrier concentration is Ni. Let us, I am taking silicon. Ni for silicon is practically 1.5 into 10 power 10 per centimeter cube. Okay. In this example, I am taking Ni value is simply 100. 100 is the Ni value. That means number of electrons and the number of holes is equal to 100. So electron concentration is 100, number of electrons, and the number of holes also 100. Number of holes also 100. For this semiconductor, I am going to adding doping. Let us, I am doing doping. Doping, I am going to adding Nd, donor impurity I am going to be adding. I am going to adding 900 impurity atoms. 900 impurity atoms. These 900 donor impurity atoms donate 900 electrons. These 900 donates 900 electrons. It doesn't provide any hole to you. It doesn't provide any hole to you. Now 100 plus 900, 1000 electrons, and number of holes are 100. So by doing the doping, by increasing doping, let us, I am going to increasing the doping. That means I am going to increasing little bit 900 plus, and now it became, let us 905, now it became 1005, now it is 100 itself. So from this, what we understand, by increasing amount of doping, majority carrier concentration is increased from 100 to 1000. See that? So if you want to increase majority carrier concentration, just increase the amount of doping. If you want more sweet your milk, just add additionally one more sugar spoon into that. Okay, so just by increasing amount of doping, majority carrier concentration is increasing. Very simple. Now you need to work out on this. From this, you are saying minority carrier concentration, no change in minority carrier concentration, you are saying, but that is wrong. That is wrong. Why? Because see here, in a semiconductor, just take your semiconductor. In this, at the time of intrinsic, you have electrons and holes. Okay, now once you are adding Nd, phosphorus into this, you are adding phosphorus into this in the sense, externally you are going to adding phosphorus ions plus electron, additional electrons you are adding into that. Now these electrons are going to, some of these electrons are going to forming covalent bond with this. We call it as a recombination, forming covalent bond with this. Okay, so once it is a covalent bond, that means a recombination, that pair will disappear. Okay, so you need to add that recombination. Now number of recombinations. Let us take recombinations of 35. So I am giving negative polarity to that. Why? Because after recombination, that pair is going to disappear. After recombination, that pair is going to disappear. That's why I am giving negative polarity to that. Now 1000 minus 35, 965. 100 minus 35, 65. From this, by increasing temperature, by increasing amount of doping, majority carrier concentration is, see this, initially it is 100, now it is 965, so it is increased. So by increasing temperature, majority charge carrier concentration is increasing, and your minority carrier concentration is initially 100. Okay, and after doping, after adding impurity, due to recombinations, you are losing some of the minority charge carriers. Now finally, the net minority charge carriers are 65. That means compared to initial value, it is less. So here, decreasing. So the one important point we can conclude from this is, by increasing amount of doping, majority carrier concentration is increasing and minority carrier concentration is decreasing. Okay, so I will write that point. Please take a note of that. It is very, very important point, sir. It was asked previously in examinations also. in all competitive exams, more or less it was asked previously. Okay, so take a note. First point is, in a semiconductor, take a note. First point is, in a semiconductor, by increasing amount of doping, majority carrier concentration increases, and minority carrier concentration decreases. Sir, this is very important point, sir. P carrier concentration decreases. Okay, I want to increase the minority carrier concentration. What I want to do? My intention is to increase the minority carrier concentration. For that, what I want to do? Simple. Break the covalent bonds. Let us. Previously, we done one analysis. I am going back to that a little bit while. See here. In this, let us increasing temperature. I am going to increasing temperature. So let us, by increasing temperature, 50 covalent bonds were broken. Let us, 50 covalent bonds broken. So once 50 covalent bonds are broken, 50 electrons and 50 holes both are generated. Now it is a plus 50. So it is a 5010, 1005, sorry, 1015. 1015, and here it is 115. Okay, see here. Now it is increased from 65 to 115. Okay, worst case, if you take even 10 increment, that is 10 increment, it became 975, and it became, let us, I am taking only 10 covalent bonds because the comparison is more here. That is the issue. Now it is 75. So it is a 75. Now see this. So by increasing temperature, your majority carrier concentration is increased from 965 to 975, and minority carrier concentration is increased from 65 to 75. You may ask one thing, sir, just before you mentioned to increase minority charge carrier concentration, temperature has to be increased. But by increasing temperature, not only minority, majority carrier concentration also increasing. Yeah, it is increasing. But if you observe percentage of increment in majority and minority compared to percentage of increment in minority, percentage of increment in majority is very less. Here it is increased from 65 to 75, but here it is increased from 965 to 975. Okay, here percentage of increment is very less compared to here percentage of increment. So when temperature is increasing, both majority and minority charge carriers are increasing, but compared to the percentage of increment in minority charge carriers is very high compared to percentage of increment in majority charge carriers. Because of this, we are not giving the priority to increment in majority charge carriers at the time of increasing temperature. Okay, so far you are in a position to control the number of charge carriers in a semiconductor. Once number of charge carriers are under your control, your electronic device should be under your control. See, if you want 100 electrons to get a conduction, 100 electrons conduction is sufficient for your application. So according to that, you provide 100 electrons to your semiconductor. According to that, you add little bit amount of impurity to that. If you are increasing amount of doping, more number of electrons you get. So then it will provide more amount of conductivity. Okay. So based on the application, how much conductivity we need to get this much conductivity, how many charge carriers we need to get this much charge carriers, impurity I want to add. For example, minority charge carriers are not sufficient to me. Okay, I will increase little bit temperature. So now your semiconductor is under your control. So once a semiconductor is under your control, you can design any electronic device based on your requirement. You can design it. I want more conductivity, I will add more impurity, then I get more number of charge carriers. Okay, I want less conductivity, I will add little bit amount of impurity, then I get less number of charge carriers and I get less conductivity. Okay, so like that you can control the number of charge carriers in a material. Okay, by changing the doping or by adding impurity into that. Is it okay? And here one more thing. Let us take a cup of milk. I am adding 1 spoon of sugar into that. Okay, it is good. And generally children take more amount of sugar. So I am adding one more spoon of sugar into that for my children, for my child. Now it is sweet, fine. If you add one more amount of sugar into that, then you have to said it is a sweet, it is not a milk. Then you have to said it is a sweet. Okay, the way how the property of the material is changing by adding impurity by adding sugar into that, the same way by adding amount of impurity here, the property of the material is changing. Previously we observed energy gap, acceptor energy level and donor energy level ED. Okay, simple example, simple. I am taking intrinsic semiconductor. Let us I am adding one spoon of impurity. Let us it is my PN junction diode. So from this semiconductor I can made PN junction diode. Okay, now I am adding one more impurity, one more amount of impurity. That means one more spoon of impurity to this. After adding one more spoon of impurity to this, now it has high impurity, more impurity you added. Then this material can be used to design your Zener diode. Zener diode. Okay, now I'm adding one more spoon because I want to make my made sweet. I'm adding one more spoon. Now 3 spoons of impurity. Now impurity is very high. Now by using this material you can design tunnel diode. See this, how simple it is. One amount of spoon, 1 spoon of impurity, PN junction diode. One more spoon, Zener diode. One more spoon, tunnel diode. PN junction diode used as a switch and using in rectifier circuits. Zener diode used as a voltage regulator. Tunnel diode used as a high speed switching device. High speed switching device. The switching speed of that device is more than regular PN junction diode. Okay. Now next one is, so tomorrow we discuss about mass action law, and based on this knowledge so far what we completed analysis here, we give some polarity to a semiconductor. If you take a semiconductor, what is the polarity of that? We discuss about those things. Okay. Last but not least, so once again we are welcoming you all to Unacademy platform. Okay. So to subscribe this, by using my code VRAW10 you get 10% discount, and by hitting this balloon symbol, okay, you get the notifications about my classes. Okay, and you can join in telegram group also by selecting this one. Okay, so if you have any doubts or any queries, you can give that information through YouTube comments. Okay, I will clarify those things in the next session. Okay, thank you very much. Thanks for spending your valuable time with us. Okay, so please don't forget to use my code while subscription, VRAW10. Okay, please don't forget. Thank you very much.